I'd like to start this year with the last problem from the midterm that we studied, that we did before the break. And that's number 14 here. And what we have is we have a transformation of the default value, the default rational function, or the default hyperbola. We picked this problem. It's a good sort of segue from the last problem of last semester to the first problem of this semester. Also, we need to make sure that we have a pretty firm foundation with rational functions. I understand that they're underrepresented in the textbooks that we use, and they feature more prominently on the HL syllabus in the DP course. So it's a good review for those of you who struggled with it. I know a lot of us did, and also, it's the coming off of a 3-week break. You may have forgotten a lot. So we will begin here. We'll work this problem, and then we'll look at some problems we did for homework as well last year in the first semester, which go the other way. They give us a function and ask us what's been done to it. This is giving us the function and telling us to do things to it, to do certain transformations to it, and find out what we end up with. And then I'd like to discuss a shortcut that I found, some other ways of looking at these things that I thought were interesting. So that's what we'll do now. There's another video that I've linked in the lesson as well from Mr. Chun. It's about a 15-minute video that deals with more complex rational functions, dealing with nonlinear numerators and denominators. But if this is something you feel like you've got a handle on, you think you got this one right, the last one on the midterm exam, you can skip to the end and look at the synthetic division part that I added, and then go ahead and look at Mr. Chun's video on more complex rational functions and how to graph them. So let's get started here. We've got this rational function, and we know we've done a couple of things to it. So we're being told here in this problem that we are going to do 3 things. We're going to, first of all, we're going to stretch. We're going to stretch this with a scale factor of 1/3. That's simply multiplying by 1/3. We're going to reflect it in the x-axis. We're going to reflect it over the y-axis. It says y-axis here. So that means swapping x for negative x. And then we're going to translate it, move it to the right by 2 units. So let's do this piece by piece. We got 3 things we need to do to 1 over x. So the first part is this stretch, and that is a scale factor, and they can be positive or negative. This one, they can be positive, negative, or they can be greater than 1 or less than 1. This one, we are just going to take the scale factor gets multiplied by the function. So that's simple enough. That's going to give us 1 over 3x, 1/3 x. The second part, the reflection in the y-axis, just means to replace x with negative x. That reflects it across the y-axis. So the second step is just going to give us negative 1/3 x, because I just replace x with negative x and it comes out. And then the final step is going to be 2 units to the right. So moving something 2 units to the right means from the x, directly from the x, I need to subtract 2. So it's not going to be this, right? It's going to be 1/3. It's the negative 1/3 that I've already worked out, x minus 2. So this is going to give me my translation to the right of 2 units. And simplifying this expression, I'm going to get negative 1 over 3x minus 6. So that is the answer that I get for part A. This is written in the standard form of a rational function. That's part A. So part B is going to ask me now to find my asymptotes. So my asymptotes are going to be the horizontal one and the vertical asymptote. The horizontal asymptote is going to be what this graph of, this is now g of x, I think we're calling it. So we have g of x here. The graph of g of x as x approaches infinity. So either positive infinity or negative infinity, either way, this function is going to go to 0. It's 1 over a very large number, or negative 1 over a very large number, but it's still 0. So there's been no horizontal displacement. There's been no vertical displacement because the horizontal asymptote hasn't moved. The vertical asymptote is going to be now for our standard 1 over x. It's at 0, but now it's when this denominator here is 0. Well, that's going to be equal to 0, which is unallowed, when x is equal to 2. You could look at it over here as well, right? So x minus 2 cannot equal 0, so x cannot equal 2. So the vertical asymptote is at 2. The vertical asymptote is the vertical line, so that's going to be x equals 2, and then this is y equals 0. All right, so those are the asymptotes that we have. And then the domain and the range, well, the domain and the range are going to be all real numbers except the asymptote. So for part C, we're going to have the domain is equal to the set of x such that x is not equal to 2 and x is otherwise all real numbers. And the range is going to be equal to the set of all y such that y cannot equal to 0 and otherwise y is all the real numbers. And for part D, we want to sketch this thing. We could take the standard parabola, which looks, the standard hyperbola, which looks like this here. And we could do the things to it that we have been told to do. We could stretch it by 1/3, which means actually bringing it down, right? If this is 1, 1, then this new one would be 1, 1/3. This new point would be somewhere like around, it would be over here at 1 and something around here, right? Like at 1/3. Now, we also need to flip it though. So this thing has to go from this side of the y-axis over here. We're on this side of the y-axis over to this side of the y-axis. And then there was also a vertical shift. We took this thing as a horizontal shift. The vertical asymptote shifts from here, and the vertical asymptote is going to shift horizontally over here to 2. So I could do all those things, and if I do, I should get something that looks like this right here, this red graph. Okay, so I'll turn this one, I'll leave that one on, and that is what we should get. So the green graph has been pushed over the y-axis, and then it's been shifted to the right by 2, and you can see that it's been actually made a little bit, it looks shallower if you like. Here, this goes up a lot more quickly, this goes down more shallow. And if you look at points along there, you should be able to pretty much tell that. So if this is 0.11, roughly it's there 1, 1, over here, this point is what? 1, it's 1, 1/3. And that's the scale factor at work. Okay, so that problem is done. And what I'd like to look at now is some of the other problems we did for homework, which are this problem in reverse. And that means, for example, let's look at problem number 4A, which was a homework problem last year. And when we did this, what we wanted to do, so instead of being told what's being done in terms of geometric transformations, we're given this equation, and then the question is, well, what had to happen to 1 over x to make this? How did we get from here to here? What went on here? And the way that the examples work through it in your book is to take this and split it up so that I get a constant term. without any variables in it, with no x's in it at all. So in order to do that, I would do some manipulation to the top of the function, to the top of the fraction, so that I can split it apart. So let's look at that way, the way that the book just sort of goes through it by playing some algebraic manipulation. I would take, and I'm going to want to get an x plus 1 to factor out of the top and the bottom so that I can cancel that. Well, how am I going to do that? I've got a 2x up here. If I got a 2x up here and I want to factor out an x plus 1, I'm going to need a 2. I'm going to need this 2 right here. So if that is what I have, then I'm going to want to also subtract 2. I can't just add 2. I can add 0 though, and so that's the same thing as adding 0. And of course I've got the 3 over here. So when I do that, now I can regroup and I can say, and this is now still all over x plus 1. And now I can regroup and I get 2x plus 2 over x plus 1. And then this is here, this is going to be plus 1 over x plus 1. Okay, and I regroup these this way, and then this was left over here. So this 2 comes out, and I want to rearrange this. I'll put this over here. So I got the 1 over x plus 1, and then this thing here, it reduces to just 2. So this tells me that I have from, let's see, 4a here, that what's happened? Well, I have taken this, and here you can see where we have shifted to the left by 1, and then this is going to be a shift of 2 up. So in terms of a translation vector, it would look like that. And that's what's happened. And there hasn't been any scale factor added here. Another way that I could do that, though, is I could sort of look at it from what's happened to the asymptotes. Let's look at it that way. Let's look at it graphically. So if I were to take back up here and look at this again, I would say, well, I know that here, of course, the horizontal asymptote is 0 and the vertical asymptote is 0 for my standard hyperbola. But for here now, the horizontal asymptote has gone to 2. The limit, or the ratio, of the x terms is 2. And now the vertical asymptote is when the denominator is equal to 0, so that's -1. And if I were to look at it that way, then I would say, well, so I've taken 1 over x, and then I have shifted it to the left by 1, so that's going to be x plus 1, and then I shifted it up 2. Okay, so let me write that a little bit neater. I took 1 over, and this was the horizontal shift because the vertical asymptote shifted over to -1, to the left by 1. So I add 1 here, and I've gone up by 2. And now that's really a simple way to get to the answer without having to do this algebra. If I were to go the other way and confirm this, well, I'm going to get, what does this become? This becomes 1 over x plus 1, and then this is going to be 2x plus 2 over x plus 1. And then so this whole thing is 2x plus 3 over x plus 1, which is where I started. Okay, so that's kind of a shortcut. But now let's look at maybe 3a, which was also a problem that we did for homework last year. So same exercise, same page, 3a. 3a ask us to look at what's happened to 2x plus 4 over x minus 1. Well, what if I try my shortcut here? If I try my shortcut instead of going through and doing the algebraic manipulation, I'm going to say, well, what's happened to 1 over x? What's happened to 1 over x to make this to go from here to here? I have taken my vertical asymptote to 1, so the horizontal asymptote has gone to 2. So the horizontal asymptote has gone to 2, this ratio here, and the vertical asymptote has gone over here to 1. So that means that I've taken 1 over x, and then I have shifted it over to the right one, so that's 1 over, shifted it over to the right, and then I added 2. I went up 2. If I go through and try to simplify this, this is what I'm going to get. I'm going to, if I try to put this as a proper rational function, I'm going to get 1 over x plus 1. And then this is going to be plus 2 times x plus 1. But this is a minus, so let me make sure I got that right. So I have my 1 over x minus 1, and then I have over here plus multiplying top and bottom times x minus 1. I got this. So now this is going to give me 1 plus 2x minus 2, and that's all over x minus 1. And this is going to be equal to 2x minus 1 over x minus 1. And that is not the same thing. This is not the same thing as this. So what happened? Well, I neglected the stretch. So there's a stretch factor in here that hasn't been accounted for. The transformations have been accounted for, but this expression and this expression here and this expression here, they're not the same thing. Let's go back and look at this the way that the examples in the book have been worked. And so remember what they did is they would take 2x plus 4 over x minus 1, and then we would say, well, we've got to get an x minus 1 out of this thing. So I'm going to have to get a 2x minus 2. Well, if I have a minus 2, I better add 2, and I've already got this 4, and now this is all over x minus 1. And I can regroup, and what I get is I get 2 times x minus 1 over x minus 1, and then this part here is going to be plus 6 over x minus 1. This, of course, goes to 2, and then swapping the terms so it's in more standard form, I get 6 over x minus 1 plus 2. So I've got my translation now. I went over to the right 1. I went up 2, but now I've gotten my stretch factor. Well, when I tried the shortcut just by looking at how the asymptotes have moved, that doesn't account for the stretch factor. But as I was playing around with this, here's something I noticed. If I were to take x minus 1 and divide it into 2x plus 4, this is what I get when I do the synthetic division. I come up here and I get 2, and then this is going to give me 2x minus 2. So 2x minus 2x is 0, and then 4 minus negative 2 is positive 6. This gives me my stretch factor. So I tried this again with a couple of other ones. So for example, 3b. 3b was, the question was 3x minus 2 over x plus 1. So what's happened here? Well, I see that my horizontal asymptote has gone to 3. So the horizontal asymptote has gone from normally 0 to 3. So that's been shifted up. That's a vertical translation up. And then, of course, here my vertical asymptote has gone over here to negative 1. But there's a stretch factor. I could go ahead and rewrite this thing this way, but then it wouldn't be equal. If I were to just go and say, okay, well, that's 1 over x plus 1 plus 3. This will not give me this because I'm missing the scale factor. You can try this yourself. What is that scale factor going to be, though? Well, it turns out if I take x plus 1 and divide it into 3x minus 2, this gives me 3. I guess goes in 3 times. I get 3x, and then I get plus 3. 3x goes away. 3x minus 3x is 0, but negative 2 minus 3 is negative 5. So if you were to look up the answer, you see that there is a scale factor and a reflection. You can do this again for 3c as well, and then you get positive 5. So I would expect the quotient here and not the remainder here to give me the stretch factor, but oddly enough, it's the remainder that gives you, not only will it give you the scale factor, but it'll also tell you whether or not it's been reflected. Now, this has its limits, and for example, if you were to look at 4D, you see that there's a problem. So if this interests you and you're kind of like me, you're curious about why this works and how this works, try 4D and look at the answer and see what you think. You have to make sure essentially that the coefficient on the divisor is going to be equal to 1 for it to work. But it seems to work. It's worked for several problems that I've tried. So look at that if that interests you, and if you're, you should all watch Mr. Chun's video, which is a link below, on more complicated rational functions with holes in them and that don't involve simply linear, nonlinear numerators and denominators.